Hello, welcome to Biology 1114 again at Rogers State University. I'm Dr. Keith Martin, your professor for the course. We're starting a new section here in our unit. This is Chapter 2, and it's only going to be the first part of Chapter 2, and it's going to be a little bit of review for most of you. I would assume most of you have had a little bit of chemistry in high school, junior high and high school, your physical science class and your biology classes. Maybe some of you even took a chemistry class in high school. So this is going to be a review for some of you, but others of you, this is going to be brand new, and so it's going to be hard for you to kind of follow. So you may have to watch this lecture a couple of times to really kind of figure out certain parts of it. But some of you, it's going to be pretty elementary, and you're going to be able to follow along real quick. So this is Chapter 2. Chapter 2 is the chemistry of life. And so let's begin to walk through some of this. Very basic here. If you remember from junior high and high school, your definition of matter. Remember physical science class in junior high and other classes you took in high school, you defined matter as basically anything that has mass and occupies some space. Well, that's pretty much everything, okay? In fact, if you kind of stop and think about it, is there anywhere where there's not matter? If matter is anything that has mass and occupies some space, well, that's basically everything. But there are a few places where matter does not exist. Some of you have already answered this in your mind. Space, or in what we call a vacuum, there's no matter. And so it lacks anything that has mass or occupies space. And so yeah, outer space is between the planets, between the intergalactic materials. There's nothing, just nothing. So there's no matter. But here on Earth, basically, hey, there's even matter that you can't see and you can't feel and you can't smell. You're breathing in matter right now, oxygen, nitrogen that we've already talked about, some ozone, and some other chemicals in the air. So yes, even out here that we can't see, feel, or taste, matter still exists because there's atoms there. You simply can't see them or smell them or touch them. So matter is comprised of elements. You remember these elements from your previous science classes. An element is a substance that can't really be broken down by chemical means into other substances. Now, it's made up of atoms, and we can kind of break down atoms, but not naturally. We can do that in laboratories, but not naturally. So living things, plants, animals, fungus, bacteria, all living things is comprised of elements and atoms of those elements. Here's 6 listed for you here. In fact, 99% of all living matter is comprised of these 6 elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. I usually flip the nitrogen and the phosphorus, and it's schnapps: carbon, hydrogen, oxygen, nitrogen, phosphorus, and then sulfur. But almost all matter on Earth that is living matter, life, is comprised of these 6 elements. So we need to be pretty familiar with these 6 elements. You remember this? Yeah, this is a periodic table. And this is an abbreviated form of a periodic table, but it lists all of the elements known to exist. Hey, not just on Earth, but all elements known to exist in the entire universe, all the way out past Pluto even. And the gaseous elements, the big ones, Saturn and Jupiter. We know the sun. We know what elements comprise those substances. So, but there's about 104 elements. About 114 elements, all the way up to maybe about 117 now, because there are laboratories all across the world that try to create new elements. But there's about 92 natural elements that occur naturally on the earth and in life, and the rest are synthetic elements. But there's about 92 natural elements. All of these elements have a symbol. For instance, we have several of them highlighted here for you in dark blue: hydrogen, carbon, nitrogen, oxygen. Those are the big 4. Those are the big four: carbon, hydrogen, nitrogen, and oxygen. They're bold blue color here for you. They all have the elements of C for carbon, H for hydrogen, nitrogen, N for nitrogen, O for oxygen. So every element has a symbol. Notice the light kind of pastel blue elements on this periodic table. Those are elements that are not necessarily used in large amounts, but they are what we might call trace elements. Look at the legend on your slide there. These are elements that are less abundant, but they're still bulk elements. In other words, your body uses them. We know about the big four: carbon, hydrogen, nitrogen, and oxygen. But the other pastel blue ones here are elements that are still bulk elements that we use a lot of, but just not in large amounts. Sodium, potassium, magnesium. I take supplemental magnesium tablets. Calcium, obviously, phosphorus, sulfur, chlorine. All of these are used by living organisms, but not to the extent of the big four: carbon, hydrogen, nitrogen, and oxygen. The other elements here in green, these are trace elements. These are elements that are used by living things in very small amounts. So we call them trace elements. Copper, zinc. You may take your Flintstone vitamins, which have a lot of copper and zinc in them. Manganese, iron. All of these are used by our bodies, but they're used in smaller amounts. So that's what a periodic table does. It lists all of the elements all the way up to the 92 natural elements and then beyond the synthetic elements as well. Some symbols are a single letter, like CHNO. Some elements have a double or a two letters, and like sodium, Na, calcium, Ca. And that's how so the symbol of the element is how we identify where it is on the periodic table. Now, there's more on this periodic table other than just the symbols. And we're also going to talk about why they're arranged the way they are on the periodic table. And so moving on, it shows us, the periodic table shows us properties of atoms or properties of elements. For instance, look at the first one here. Number 1 is hydrogen. Symbol is H, but notice it has a number. At the top is 1. That's the atomic number. Here in a minute, we're going to learn that that tells us the number of protons of that particular element. Hydrogen is the most simple, and so it only has 1 proton, but it also has a weight assigned to it. Now, we don't measure atoms in pounds or grams or micrograms or nanograms, even. Very, very small, what we call atomic units, AMUs, atomic mass units, or how we measure the mass, not necessarily the weight, but the mass of an atom. So in this box on the periodic table for hydrogen, it gives us a symbol. H gives us the name. It gives us an atomic number, which is the number of protons we're going to learn here in a minute. And then it gives us the atomic mass number, or the atomic weight, which is 1.0079, or essentially 1 atomic mass unit. So every one of these elements has that information. If you look across over here to carbon, there's C. The atomic number, 6, tells us the number of protons. And then the atomic mass, or the atomic weight, is 12.012. Notice as we progress across and down, the number of protons get more and the atomic mass gets heavier. So as we move to the right and down the periodic table, the atoms get heavier, their mass gets more, and their subatomic particles get more as well, a little bit more complex. So let's talk about these structures that make up the atom. Again, this is going to be a review for many of you because you've had this in previous classes in your scientific experiences. But the atom is the smallest piece of an element that retains all of the characteristics of that element. All of the atoms of hydrogen basically look the same. All of the atoms of nitrogen basically look the same. It's because they all have the same number of elements. And But we're going to look here. So notice here they are. It's what we call the subatomic particles. It's comprised of protons, neutrons, and electrons. Here in the center of an atom is what we call the nucleus. The nucleus contains protons and neutrons. The atom also has electrons. We usually designate it by an E negative. And these electrons move around the nucleus in very specific distances from the nucleus. We call these shells or orbits, like the planets orbit the sun. So those are the three particles of an atom: protons, neutrons, electrons, and then the area is the nucleus. The center part is what we call the nucleus. And all atoms, all known atoms of elements, have these similar structures. So let's learn a little bit more about these. Here's electrons. So there's protons, neutrons, electrons. Here's electrons. Electrons surround the nucleus. They're very small, they're very fast, and they're very light. In fact, they are so light, they nominally contribute to the mass of an atom. But what does contribute to the mass of the atom are protons and neutrons here in the nucleus. Now, that atomic number tells us the number of protons and the number of neutrons and kind of the number of electrons too. That's what the atomic number tells us. Now, a little bit more. Let's get more specific. The electrons in an atom, they are negatively charged. The best way to explain this is there's some polarity to almost all substances. But did you ever play with magnets as a kid? When I was a kid in the 60s, we played with magnets, okay, and rocks and sticks and things. But magnets have a polarity to them. You know this. For instance, I used to have some horseshoe magnets shaped like a horseshoe, and you put them together one way and they would stick. But if you turned one over, it would repel. And you know this. Like charges attract, opposite charges repel. Well, electrons are the negative polarity part of atoms. Protons are positively charged particles of atoms. Neutrons are just neutrally charged. There's no charge. They do have some mass, but they have no charge. So there's three structures in every atom. Electrons have a negative polarity to them. Protons, positive polarity to them. Neutrons, no polarity. They're neutral. Notice what contributes to the mass of an atom. The neutrons and the protons. Notice where they're located. In the center of the atom, in the nucleus. Look at these electrons. They contribute negligibly or nominally to the weight or the mass of an atom. And they move around the atom in very specific orbits. And so here we are again, back to the periodic table. The atomic number at the top of every box in every element, that's the atomic number. It tells us the number of protons, specifically the protons. The number of electrons tend to equal that, naturally speaking, or theoretically speaking. So carbon here has 6 protons, nitrogen 7 protons, oxygen 8 protons. So you get the drift here. As we move across and down, we obtain more atomic particles, and so the mass gets heavier too. So the atomic number tells us the number of protons. Okay, the atomic mass is determined by the protons and the neutrons. It's not necessarily double. Remember what 6 was? 6 was carbon, 6 protons, 6 neutrons, 6 electrons, but it's only the protons and the neutrons that actually contribute to the mass of the atom. 6 protons, 6 neutrons. So let's talk about this. Number of protons never change. in an element. If carbon has 6 protons, every carbon is going to have 6 protons. Uranium has the same number of protons but some atoms have differing numbers of neutrons. You know some of these. If it has differing numbers of neutrons, then it has different atomic masses. You've heard of this, especially when we are dating archaeologically rocks or plant material or living things or dinosaur bones or whatever. The way we determine, you've probably asked this, how did they determine the age of these prehistoric or whatever items? And we determined the amount of breakdown of different weights of the same element or the same atom. For instance, carbon 12 versus carbon 13 versus carbon 14. All of these carbons have the same number of protons, but they have differing numbers of neutrons. So they have different weights and they break down in different periods. Their shelf life is different. So we call these isotopes. Carbon isotopes are isotopes that are all carbon, but they have differing numbers of neutrons, meaning they have different weights. There's different isotopes of iodine, different isotopes of uranium. Not all elements have isotopes of themselves, but carbon, iodine, uranium are a couple that do. They have the same number of protons, just different numbers of neutrons, which means they weigh differently. So those are what we call isotopes. But we have to talk about this. We have to talk about chemical bonds. Most elements, they don't just hang out by themselves. We normally just don't go out and find oxygen or nitrogen or carbon by themselves. Almost always they are linked to other atoms, atoms that are linked together. For instance, what we have depicted here in red and gray are water molecules. Now, we don't have it here, but red is usually when we draw these molecular structures, red is normally oxygen. Light beige or light blue, light gray, whatever this is normally hydrogen. This is one oxygen atom, 2 hydrogen atoms. You know that as H2O. This is water. And normally we don't see water, we seldom see hydrogen and oxygen just out there by themselves. Normally they're bonded together or linked together. And even adjacent water molecules are bonded together. So these links are very important. This is where the confusing part kind of comes in, because the way atoms are linked together are different. They're not all linked together the same. Their properties determine how they are linked together. Now we call these bonds, how they are bonded together. So let's talk about some of this. And some of you have had some chemistry. This is going to be a bit of a review for you, but let's walk through this. So here we are with several elements here. Here's hydrogen with 1. Hydrogen is the most simple. There's carbon with 6 protons. That's what the P stands for. In fact, normally we put a little plus right there because protons are positively charged. Look at nitrogen. It's number 7 on the periodic table. It has 7 protons. Oxygen is 8. It has 8 here, and so on. So you understand what we're doing here. Now, really, we don't care that much about protons. We really don't care that much about neutrons. But the electrons, we have to talk about the electrons of these elements, these atoms, because it's the electrons that give these atoms their properties. It tells us how they link together with other atoms. So we have to talk about these electrons. Remember, they're negatively charged, slightly attracted to the positive charges in the nucleus. So opposites attract. So we have electrons flying around these nuclei, and then we have a positive center. So that attraction between negative and positive is what holds atoms together. But these electrons, they don't just move randomly around the nucleus. They move in very specific orbits or very specific shells. These orbits that are close to the nucleus are kind of small. Just like the orbit of Mercury around the sun is not the same distance as the orbit of Jupiter around the sun. Jupiter's orbit is much wider, much further away, and much longer. That makes sense, doesn't it? Same way with atoms. These electron orbits close to the nucleus are very small. Now, electrons are negative charged. Okay, so as we get more electrons, they tend to push each other away. Remember, similar charges, okay, repel each other, opposite charges attract. As we get more electrons in these atoms, they tend to push each other away. So this orbit is the most simple. It is the closest orbit to the nucleus. It's small. It doesn't occupy much area or space. And so fewer electrons are found here. In fact, a maximum of only 2 electrons are found in this small, close orbit to the nucleus. As atoms get more electrons, for instance, carbon, there's 6 protons. There are 6 electrons. Well, but this orbit close to the nucleus is so small, it can only house 2 electrons. Any other electrons are repelled further away from the nucleus into what we call a second orbit or a second shell here. It's bigger, occupies more space, it can occupy more electrons. In fact, up to 8 electrons can be found in the second orbit. Hey, moving on to nitrogen, 7 protons, 7 electrons, they match. Remember, 2 in the first orbit, close to the nucleus, small, close. 8 in the second shell or second, it doesn't need 8, it only has 5. 1, 2, 3, 4, 5. Here's oxygen, 8 protons, 8 electrons, 2 electrons close in this small orbit, and then there are electrons in this next orbit out here. Okay, it can hold 8 before it repels even more out here. Look at this element here, 15 protons here in the nucleus, 15 electrons, 2 in the closest, smallest orbit, 8 in the next orbit, and then it kicks 5 more out to this orbit out here. So you understand what we're saying here. The close orbits are small and contain fewer electrons. It kicks or repels electrons further away if they have more. Repels them even further away if they have more. And so these are very specific shells or orbits. It's what we call the Bohr model. Okay, we say it this way: there's 1 electron in hydrogen's orbit of electrons. Okay, in carbon there's 2 and 4. There's 4 in the outermost orbit of carbon's atom. Nitrogen, there's 7 protons, 7 electrons, 2 in the innermost, 5 in the outermost orbit or shell of electrons. So it's 1 here, 4 here, okay, 5 here. Oxygen has 8 protons, 8 electrons, so it's 2, 6. There are 6 in this outermost orbit. That outermost orbit here, the second one, holds a maximum of 8 electrons before it repels more electrons further away. So we have 15 protons here. Okay, we have 2, 8, okay, and then 5 in the outermost orbit. As we get more electrons, they're repelled even further away into further orbits out here. These are energy shells, and this is where electrons exist. So let's talk about this. Atoms are most stable when their outer shells have no vacancies, or we could say it this way, their outer shells are full. Look at this right here. Hydrogen has one proton, one electron, but this orbit here can hold a maximum of 2. So we have a vacancy here. Look at carbon. Carbon has 6 protons, 6 electrons, 2 in this closest orbit. And look, 1, 2, 3, 4 in its outermost orbit. But this outermost orbit can contain a maximum of 8. So carbon has vacancies here, 4 vacancies. Look at nitrogen. 7 protons, 7 electrons, 2 in the innermost orbit, 5 in the outermost orbit. So that means there are 3 vacancies here. We move out to oxygen. Oxygen has 2 electrons in its innermost orbit, 6 in its outermost orbit, meaning it has 2 vacancies. See that? Atoms whose orbits are full, 2, 8, or 18 in the third orbit, like here with phosphorus. So if they have those outermost orbits full, they tend to be very stable. We call them noble. And they don't tend to react with other elements. They don't tend to bond or link with other atoms. On the periodic table, they are on the far right-hand column of the periodic table. Neon, argon, krypton. These are very stable elements. They're gases. We call them noble gases. And it's because their outermost orbits are fully occupied. There's no vacancies. They have 2 here. They may have 8 here. They may have 18 here, but they're full. Okay, neon, argon, krypton are similar elements, but most atoms aren't like that. Most atoms have vacancies in these outermost orbits, and that's important for us to know. For instance, look right here. Bonding or linking with other atoms. For instance, look at this one right here. Here's carbon, 6 protons, 6 electrons, 2 in the innermost orbit because it's small and it's close, and only 2 can remain there. The rest are kicked out to this next orbit where there's only 4 out there because there's only 6 total. So there's only 4. In order for carbon to be stable, it doesn't need 4 in this outermost orbit or shell. It needs 8. It has 4 vacancies right here. Carbon is often linked with hydrogen. In fact, one of the most common bonds on Earth are the hydrocarbon bonds. You've heard of hydrocarbons. This is one of the most common bonds on Earth between hydrogen atoms, carbon atoms. One is because they're very abundant elements on the Earth. So let's look what happens here. Carbon has 4 electrons in this second orbit. That is not a stable energy level. It has 4 vacancies. Hydrogen. Every hydrogen atom has 1 proton, 1 electron, but this orbit around hydrogen has a vacancy. So what happens between hydrogen and carbon is that they share electrons. Hydrogen will share its electron with carbon. Carbon will share its electron with hydrogen. And so we are getting closer to stability. If we have 4 hydrogens, and there's an abundance of hydrogen in our atmosphere, if we have 4 hydrogens, all of them willing to share an electron with carbon, carbon is willing to share an electron with each of those hydrogens. So here's what we have. We have a carbon bonded with 4 hydrogens, one of the most common gases on Earth is methane gas, CH4, 1 carbon, 4 hydrogens. Look what's happened here. Every hydrogen has its electron plus an electron shared from carbon. See that? So now we have a very stable configuration. Hydrogen's orbit has 2 electrons most of the time. Carbon's orbit, outermost orbit, has 8. This is what causes linking. This is what causes bonding between elements. And so this is how we talk about linking or bonding. Atoms without vacancies are stable. In this case, every carbon in this bond has, and there's only one, has periodically 8 electrons in its outermost orbit, and hydrogen 2. This creates stability. This is what all atoms try to get to. Their energy levels move towards stability. And so that's what we need to talk about, are these linkings or bondings that occur. This is methane gas, one of the most common gases, the bonds that occur between 2 elements. In these kinds of bonds, where electrons are shared back and forth, we call these covalent bonds, covalent linking. These are where electrons are shared between atoms. Now, this is nice and convenient, and it occurs with a lot of different atoms. Ammonia occurs this way, where atoms are shared back and forth. In fact, most of the chemical bonds that occur inside our bodies are covalent bonds because they have a lot of carbon, hydrogen, nitrogen, and oxygen. So there's a lot of covalent bonding occurring inside our bodies. So this is where electrons are shared between one another. Water is kind of unique though. Look at the water molecule here. 8 protons in oxygen. So this is an oxygen atom. 8 protons, 8 electrons. 2 in the close, small orbit. The other electrons are repelled further away. 1, 2, 3, 4, 5, 6. That makes 8 electrons. But there are vacancies in this outermost orbit because this orbit is large enough to contain 8 electrons. So there's 2 vacancies. Can you see this again? Just like we saw with hydrocarbon a minute ago, very common bond on Earth is the water bond. Hydrogen, 1 proton, 1 electron. But its shell or orbit is more stable if there are 2, if it's full here. Okay, so oxygen is always willing to share an electron with hydrogen as long as hydrogen is willing to share an electron with oxygen. So that's where we get the water molecule. Here we have oxygen, 8 protons, 8 electrons, always sharing an electron with hydrogen, hydrogen always sharing an electron with oxygen. This is H2O, the classic water molecule. It is a covalent bond, very similar to methane that we saw in hydrocarbon bonds here in just a minute, just a while ago. The outermost orbits of these atoms are stable because of the number of electrons. So here's a term called electronegativity. It's the ability of an atom to attract electrons from other atoms. It's called electronegativity. In this sharing situation, sometimes atoms can be very greedy. In fact, the more electrons in that outermost orbit, the more greedy the atom tends to be. For instance, here in methane, carbon in the middle, hydrogens on the outside, CH4, this is methane gas, Every hydrogen is sharing an electron with carbon. Carbon is sharing an electron with hydrogen. This is a very equal sharing situation. But look down here with water. Oxygen has more electrons in its outermost orbit than carbon does. And when it comes to electronegativity, the more electrons in the outermost shell, the stronger the attraction, or the stronger the electronegativity, the stronger the ability to attract electrons from other atoms. In this case with water, it's not an equal sharing because oxygen has more electrons out here. It tends to hold on to these electrons a little bit longer. It's an unequal sharing. So electronegativity is very important when it comes to linking or bonding atoms together. Here's the classic water molecule. Sharing is going on here. Here's the methane molecule. Again, sharing is going on here. Those are covalent bonds. But here, between chlorine and sodium, again, one of the most common bonds on Earth. Okay, this is salt, sodium chloride. It's a slightly different situation. Chlorine has 2 electrons here in its innermost orbit. Look, 8 electrons in its second orbit. But look out here, 1, 2, 3, 4, 5, 6, 7, has 17 electrons in its outermost orbit. Very high electronegativity. Remember what I said? More electrons in that outermost orbit makes them very greedy. So what chlorine does is it steals an electron from other atoms. In this case, it steals an electron from sodium. Sodium has 2 electrons in its closest orbit. Out here, it only has a few, and 1 is transferred or stolen by the high electronegativity of chlorine. This is a different kind of bond than what we see over here. Here, it's a nice, complacent sharing of electrons, but here, it's a high electronegativity, close to a low electronegativity, and we have transfer of electrons that move from one atom to another. Here's the periodic table again. Here are some elements out here that have high numbers of electrons in their outermost orbits. Here, low numbers of electrons in their outermost orbits. As we move across the table, the electronegativity gets higher, hotter in this case, indicated by red. So electronegativity kind of depends on, do they share electrons or do they transfer electrons? It's all about their electronegativity. You know, some elements have kind of a similar electronegativity and they can share, but some, the discrepancy is much wider, and instead electrons are transferred from one to another. We call these kinds of bonds ionic bonds. It's a little more volatile. It's a little bit more energy involved. It's not a covalent situation. It's an ionic bond that occurs. See, this is where we show that electron being stolen by chlorine. And so this creates an imbalance in charges. And so we have an attraction between 2 atoms. Chlorine and sodium is one of the more classic ionic bonds where an electron is being stolen. One atom has a high electronegativity, one atom has a low electronegativity, and so a stolen electron occurs here, making an outermost orbit full or stable. These are ionic bonds, very classic ionic bonds. It creates a charge difference because negatives are moving from here to here. it creates, look at this, it creates charged atoms. Chlorine now has an extra electron. Sodium lost an electron, so we have imbalance in charges. So remember, oppositely charged particles are attracted. And so when you have these atoms with charges that we call ions, they're attracted to each other. Classic table salt, sodium chloride, is one of the most common ionic bonds on Earth, where electrons are transferred from one to another. It creates ions. So these are ionic bonds. Once the transfer of electrons occurs, then we have stability in charges, and electronegativity is kind of stable. But I want to go back to the oxygen molecule. Remember we said oxygen has 8 protons. It has 2 in the closest innermost orbit. The rest are pushed out to the outside. Here we go. Here's the second orbit. And there are 6 out there. Every hydrogen is always willing to share an electron as long as one is being shared back. But look at oxygen's electronegativity. Remember, the more electrons in the outermost orbit, the higher the electronegativity, the greedier the atom is. Oxygen is a pretty greedy atom. It doesn't have enough electronegativity to steal electrons from another atom like we saw in sodium and chlorine, but it does have a higher electronegativity. So in the water molecule, H2O, oxygen has enough electronegativity to hold its own electrons and those of hydrogens a little longer than normal. So this end of the molecule is slightly polarized. This end of the molecule is slightly polarized. In fact, most water molecules kind of look like a Mickey Mouse diagram. See that? And you can't really unsee it now. It's because oxygen in its greedy form tends to hold the electrons a little longer in this relationship. Hydrogen, because it is a low electronegativity, is kind of devoid of electrons. So we have what's called polar covalent bonds. They're not shared equally, they're shared unequally. And the water molecule is a classic polar covalent bond. And polar covalent bonds create some polarity and gives water some great properties that you're very familiar with. Creates pH, creates attractiveness between water and other substances. It creates properties where other substances dissolve in water. And it's all because of this polar situation. It's not an equal sharing, it's an unequal sharing and causes polarity in the molecule. But there's also bonds not just between atoms, but between whole molecules. In this case, we have a water molecule that is slightly polarized. We have another water molecule next to it that is slightly polarized, and they have an attraction to each other. Look at this. The slightly positive hydrogen end is attracted to the slightly negative end here. So we have another bond between 2 whole compounds. And this is called a hydrogen bond, a very natural bond between hydrogen and another, the hydrogen of one molecule to another atom of another molecule. We call these hydrogen bonds. We see this in DNA. We see this in enzymes or proteins. We see it in muscle cells. This is a pretty weak bond that's located between 2 different molecules. We call these hydrogen bonds. So you're very familiar with these, and this is pretty much it for this chapter. These are hydrogen bonds. But I do want you to notice this table here. This is the last slide. Here's the bonds that we talked about: ionic bonds, covalent bonds, hydrogen bond. Not too concerned here, but hydrogen bonds, covalent bonds, ionic bonds. Here's a little bit of information about each bond. Is it a strong bond? Is it a weak bond? And there's some examples here too. This is a great way to end up chapter 2. Now, there's some other things here in chapter 2, but we're not going to move on. This is all we're going to cover for this particular week.